Let me welcome you to this lecture. We are now familiar with different methods for preparation of metal alkyl complexes, and during this lecture we will learn we will discuss about few important aspects of metal alkyl chemistry, and one particular aspect or one particular important thing that was very interesting about metal alkyl chemistry is that the preparation of binary metal alkyl complexes, that is complexes containing only metal ion and only alkyl ligand with no other ligands, or homoleptic leptic complexes, metal alkyl complexes, is was difficult for a considerable period of time, and it was not achieved until very recently. So that is, preparation of binary metal alkyl complexes was very difficult. So the first metal alkyl complex was prepared in 1909, and it was a platinum complex. That is, one can prepare it from PTCl4 with methyl magnesium iodide, and its reaction essentially gave a platinum alkyl complex, which is tetrameryl. And this particular compound, or metal alkyl or platinum alkyl complex, has a very interesting structure, that is, it is cubic in nature. So one can draw the structure. That is, the metal atoms and the iodide groups occupy the corners of a cube. In this way, and the three methyl groups on the platinum atoms are present on each of the platinum. So this is the structure, that is a heterocubane structure. It has this particular metal alkyl complex which was prepared. This is the first example of a transition metal alkyl complex. So this is first example of transition metal alkyl complex. So before this, main group element alkyl compounds are very well known, and they were prepared quite early. And the first organometallic compound that was prepared in 1760 actually. That is a main group element metal alkyl complex. 1760. The first metal alkyl, that is a main group element alkyl complex, was reported, and it was prepared by this reaction of this arsenic oxide with potassium acetate. So one takes 4 equivalent of this. So essentially it gives you an alkyl arsenic compound this, and this is known as, this is 3 alkyl groups, 3 methyl groups, not 2. So this is known as Cadet's fuming liquid. Of course, the compound or preparation of the compound was carried out by Cadet in 1760, but the structure of the compound or the formulation of the compound was known much later. But this was the first example of a main group element alkyl complex, and after this Franklin prepared sometime in 1860 did a reaction of zinc with ethyl iodide. So Franklin was devising this reaction or performing this reaction with the idea that he will be able to produce zinc iodide the ethyl radical by this reaction. But of course, this did not happen, and what he obtained during this reaction was a metal alkyl complex, that is diethyl zinc he obtained. So zinc is, it cannot be considered as a transition element because this is again all the d orbitals here are filled, and that is why this particular compound also is an example of a main group element alkyl complex. Now after this, in 1900, lot of metal alkyl complexes have been prepared during this period, and one of the best example again was done by the Grignard, that is Grignard reagent, and it was prepared in 1900, that is RMGX. So Grignard's reagent was prepared in 1900, which is again a main group element alkyl complex, you see, and for this Grignard obtained or received the 1912 Nobel Prize in Chemistry for preparation of Grignard's reagent. So what we have seen over here is that preparation of main group element alkyl compounds have been achieved quite early, while preparation of binary transition metal alkyl complexes was not possible for a very long time, and that was the reason why it was assumed that the transition metal carbon sigma bond is weaker than main group element, that is MgE carbon bond. So this is the reason why, because people were not able to prepare transition metal alkyl binary complexes, while main group element alkyl compounds were very well known in early period, and that is the reason why it was assumed that these transition metal carbon or transition metal alkyl bonds were very unstable as compared to main group element carbon bonds. But this is not exactly true, because when you look at the experimental data, it tells another story. That is, if you look at the transition metal carbon or main group element carbon stretching vibration, and from the stretching vibration one can calculate the force constant, and if you look at the force constant of these these bonds, that can be evaluated, say, by using this tetramethyl compounds of silicon, tin, germanium, tin, lead, and titanium. So these first four are the main group elements: silicon, germanium, tin, lead, and titanium. While titanium is a transition metal. So if you look at the force constants of the MC bonds here, that is metal to carbon bond, and the force constant is expressed in Newton per centimeter unit, and the force constant for the silicon carbon bond you get is equal to 2.93, and for the silicon germanium it is 2.72. For for germanium carbon bond it is 2.72. For tin carbon bond it is 2.25, while for lead carbon bond it is 1.90 Newton per centimeter, while for titanium carbon bond, for the transition metal carbon bond, the force constant is equal to 2.28 Newton per centimeter inverse. So what it tells us is that the force constant, which is a measure of the bond strength actually, of different metal carbon bond for that is transition metal carbon bond is more or less comparable with the force constant for main group element carbon bond, because what you see over here for the force constant for say tin carbon bond and titanium carbon bond are quite comparable, because in this case we have 2.25, while in case of titanium we have 2.28 Newton per centimeter inverse. So the force constant essentially tells us that the transition metal carbon bond is as strong as the main group element carbon bonds, and this should not be a problem, or this should not be the reason why it is difficult to prepare binary transition metal carbon alkyl complexes. Also, if you look at the bond energy of these transition metal carbon bonds, that is, you look at the bond energy of two binary transition metal alkyl complexes. In this case, the bond energy is 260 kilojoule per mole, while in case of zirconium, what you see, the bond energy is equal to 310 kilojoule per mole. So what it essentially tells us again is that the bond energy for this metal carbon bond bond energy for this metal carbon bond is quite comparable to the bond energy for metal carbon bond in metal alkyl complexes, is quite comparable to bond energy for say metal carbon bond in metal carbonyl complexes, and that is why these complexes, these transition metal element alkyl complexes should be thermodynamically stable, and that is the case in fact. And extensive theoretical studies as well as experimental data has now revealed that these transition metal carbon bond in metal alkyl complexes are quite stable, and three important uh, aspects of these transition metal carbon bonds in metal alkyl complexes has been observed. That is, the first thing is that the energy of transition metal carbon bond is, or the transition metal carbon bond, let's not say, the transition metal carbon bond is weaker than the other transition metal main group element, that is bonds of transition metals with other main group elements like oxygen, nitrogen, fluorine, or say chlorine. So the transition metal carbon bond essentially is weaker than other transition metal main group element bond, and that is with the bond of transition metal with either oxygen, nitrogen, fluorine, or chlorine. That is the trend. And the second aspect is that the energy of transition metal carbon bond increases on increasing atomic number. So, for example, we have observed that for this titanium alkyl complex, the titanium carbon bond energy is equal to 260 kilojoule per mole, while the heavier container for the zirconium, the transition metal carbon bond energy is equal to 310 kilojoules per mole. This is exactly opposite to this trend is exactly opposite to what we observe in case of main group element carbon bond, because we know that the CC bond energy is higher than say the silicon carbon bond energy, which is higher than the germanium carbon bond energy, and the trend in bond energy for different bonds formed by carbon with different main group element essentially decreases upon increasing the atomic energy. But in case of transition elements, the trend is exactly opposite. What we observe that the bond energy increases upon increasing the atomic number. The third aspect that has been observed for transition metal carbon bond is that in case of transition metal carbon bonds, the steric effect must be taken into account. While in case of main group element carbon bonds, the steric effect does not play a big role. The reason is in case of transition, this main group element carbon bond, the number of orbitals these main group elements have which are available for bonding is only equal to 4, and that is why only 4 other substituents can be present around a main group element atom, while in case of transition elements, the number of orbitals which are available for bonding is equal to 9. That is 1 s orbital, 3 p orbitals, and 5 d orbitals are available, and that is why now the number of substituents that can be present around the transition metal ion is limited by the steric effect, and this is what also is observed in case of transition metal alkyl complexes, as only limited number of ligands depending upon the steric effect can be present within surrounding the transition metal center. And steric effect plays a relatively bigger role in case of transition metal alkyl complexes than what you see in case of main group element alkyl or main group element organometallic species. So now the reason we have seen that these transition metal alkyl complexes are indeed thermodynamically stable, but the reason why there was difficulty in preparing transition metal alkyl complexes in initial period was because these compounds have several decomposition pathways, so they can decompose very easily, and they are, even though they are thermodynamically stable, they are kinetically very labile. So or alkyl complexes, we can say that these transition metal alkyl complexes are thermodynamically stable, but they are kinetically labile. That is, there are several decomposition pathways through which these compounds can decompose into other byproducts, and that is the reason why there was difficulty to isolate these compounds in the initial days. And now any particular strategy or any strategy that you make to prepare transition metal alkyl complexes has to block these decomposition pathways, or has to prevent these decomposition pathways, and only then you will be able to isolate these transition metal alkyl complexes. So one of the most important decomposition pathway through which these transition metal alkyl complexes decompose is the beta hydride elimination. So we'll discuss about the beta hydride elimination and how it takes place, and how one can possibly block beta hydride elimination in transition metal alkyl complexes, and thus this will allow one to prepare transition metal alkyl species. So let's discuss what is beta hydride elimination. So if you take a transition metal alkyl complex, say, and if this complex has a hydrogen atom on the beta carbon atom, this is the alpha carbon atom and this is the beta carbon atom, and this particular hydrogen atom, which is attached to the beta carbon atom, we call it the beta hydrogen atom. And now this hydrogen atom can have interaction with the metal, that is so this sort of interaction where a beta hydrogen atom interacts with a metal center, we know this sort of interaction as agostic interaction. So this is agostic interaction. And this sort of concerted reactions take place where now we obtain an olefin ligand from the alkyl ligand over here. And if you look at the coordination number of the metal center, in this case, in the precursor complex over here, precursor alkyl complex, here it is equal to n plus 1 because n ligands of L type is present, and along with that there is a alkyl ligand, and so that is the coordination number is equal to n plus 1. While in case of this over here, the coordination number has now increased from n plus 1 to n plus 2 because there are now two ligands. There is a hydride ligand and it is also attached to an olefin, which forms essentially after removal of this hydrogen atom through agostic interaction. And from here, the metal can come back to the earlier coordination number, that is equal to n plus 1. And an olefin is essentially released during this reaction, and now a metal hydride complex is formed, which is again unstable and it will decompose further. So through this beta hydride elimination, metal alkyl complexes essentially decompose into metal hydrides, which will decompose further, and also an olefin is formed. So what you do is if you do a mass spectrometric analysis of your metal alkyl complexes and you see formation of a olefin, then you know that your compound is essentially decomposing through beta hydride elimination. And any strategy now to prepare metal alkyl complexes, one has to block the beta hydride elimination pathway or this decomposition pathway so that one can isolate the metal alkyl complexes as desired. So what we will see now is how one can prevent beta hydride elimination or these strategies to prevent beta hydride elimination in metal alkyl complexes so that these compounds can be prepared. And one of the first and foremost strategy that one can use is that one can one can make sure that the olefin that is released in beta hydride elimination or the formation of the olefin that is released in beta hydride elimination is either sterically or energetically unfavorable. So the first strategy is to make sure that the formation of the olefin is either sterically or energetically unfavorable. How can you do so? So one can take help of the fact that formation of double bond on bridgehead carbon atom is unfavorable as per the Brett's law. We know, or Brett's rule, that formation sorry, of double bond on bridgehead carbon atom is unfavorable. So if you take bicyclic alkyl groups and alkyl ligands, then one can prepare metal alkyl complexes if the olefin that is formed after beta hydride elimination is the formation of the olefin after beta hydride elimination is unfavorable. So one can take this norbornyl ligand and if it binds to metal center, if this alkyl group, norbornyl group, binds to metal center in this way, then formation of double bond here is going after beta hydride elimination, or even on the other side as well, is going to be unfavorable as per the Brad's law, and that is why beta hydride elimination will essentially be unfavored in this case. So by taking help of this particular aspect, it was possible to prepare metal alkyl complexes of the norbornyl ligand, and this sort of metal alkyl complexes were essentially prepared. That is tetranorbornyl metal alkyl complexes of this chromium 4, manganese 4, iron 4, cobalt 4 were prepared by using this norbornyl ligand, and these complexes were could be isolated easily as they are now kinetically not kinetically inert, because beta hydride elimination in these complexes is not favored, because the formation of the olefin is not favored, as the formation of double bond on bridgehead carbon is not allowed by the Brad's rule. So this is one of the initial strategies that was applied for isolation of metal alkyl complexes. The second strategy, to make kinetically inert metal alkyl complexes by blocking the beta hydride elimination, is to use alkyl ligands without beta hydrogen atom. So this is the most simplest thing one can do, that one can use alkyl ligands where there is no beta hydride atom is present, no hydrogen atom on the beta carbon atom, and that is then a beta hydride elimination can simply cannot take place, and the metal alkyl complexes, or the decomposition of the metal alkyl complexes formed, will essentially be can be prevented, and therefore these compounds can be isolated. So examples of beta alkyl ligands without beta hydrogen atom is methyl ligand. Similarly, you can take neopentyl, which is or one can also take the silyl container of neopentyl. That is, instead of carbon, there is silicon, and one can also take other ligands of this type where there is no beta hydride hydrogen atom, or no hydrogen atom on the beta carbon atom. So these are examples of some ligands, alkyl ligands, where there is no beta hydrogen atom and therefore complexes formed, metal alkyl complexes formed by these ligands. There can be no beta hydrogen elimination can take place in those complexes, and therefore these complexes formed by these alkyl ligands are going to be kinetically inert, and therefore they can be easily isolated. So the third strategy for isolation of metal alkyl complexes by blocking beta hydride elimination essentially involves unavailability, so making sure that there is no available coordination site of extra coordination sites on the metal. Now, if you look carefully at the mechanism of this beta hydride elimination, what we have seen that the coordination number of the metal has to increase during the process of beta hydride elimination. That is, we have seen that the coordination number of the metal increase from n plus 1 in the precursor beta metal alkyl complex to n plus 2 during the process of beta hydride elimination. That is present, and that is the reason why presence of availability of extra coordination sites on the metal center, so that the agostic interaction of the metal orbitals which are available for bonding with hydrogen, with the orbitals of hydrogen can take place essentially, and that is how the coordination number of the metal increases during the process of beta hydride elimination. And if now we somehow block or we make sure that there is no coordination site is available on the metal center, then we can definitely prevent beta hydride elimination in those metal alkyl complexes. So we will see how the availability of coordination site on the metal center plays a role in determining the stability, in determining the kinetic inertness of these compounds. So, say for example, if you take tetramethyl titanium, and if you compare the stability of this tetramethyl titanium with tetramethyl lead, what you will observe here that this compound, the tetramethyl titanium compound, decomposes at minus 40 degrees Celsius. So the above minus 40 degrees Celsius, this compound is no longer stable and it decomposes. So, but if you look at the this tetramethyl lead compound, this can be easily distilled at 110 degrees Celsius. So this is stable at 110 degrees Celsius, and that is why one can distill this compound to purify this compound, and it is quite stable even at this high temperature. So there is quite a difference between the stability of these two compounds. As we see that the titanium compound decomposes at minus 40 degrees Celsius, while the lead compound, with again 4 methyl ligands here, is stable at 110 degrees Celsius. The reason for this difference in stability is because this particular compound decomposes by increasing the coordination number of the titanium atom, while in case of the lead compound there is no orbital of lead is available for increasing the coordination number. In case of titanium, there are several orbitals. Only 4 of the orbitals, valence orbitals of titanium are involved in bonding, and that is why 5 orbitals on the titanium are still available for bonding, and titanium can increase the coordination number essentially, and it does so, or it decomposes by dimerization. That is, a dimer is formed where methyl group now bridges the 2 titanium atom in the dimer, and this sort of this titanium carbon titanium bond here is a 3 center 2 electron bond, like the 3 center 2 electron bond in case of boranes that we have seen, and that is the reason why the bond order of this titanium carbon bond but titanium methyl bond has now decreased from earlier bond order of equal to 1 in case of the monomer, and that is the reason why now methyl groups can now be easily released from this dimer here, because the 3 center 2 electron titanium carbon bonds are essentially weaker as compared to 2 center 2 electron titanium carbon bonds, and this leads to decomposition of this tetraethyl titanium compound by release of these methyl groups here. But in case of the tetraethyl lead compound or tetramethyl lead compound, what we see that the d orbitals, of course, the lead is a main group element here, and it does have empty d orbitals, but these energy of these empty d orbitals are very high as compared to the energy of the s and p orbitals. S and p orbitals in lead, and lead does not use the d orbitals for bonding here, and that is the reason now why no orbital of the right energy is available in case of this particular complex, where through which lead can increase the coordination number, and that is the reason now why this particular compound lead alkyl complex is stable even at 110 degree Celsius. And what we have seen here is that if we make sure that there is no coordination site is available on the metal center, if we block the coordination site, that is, we can do so by increasing or by making sure that the metal alkyl complex that we have that is formed is an 18 valence electron species, then it will not increase the coordination number, because for increasing the coordination number it has to violate the 18 electron rule, and it has to fill electrons in antibonding orbitals, and that is the reason why now such complexes or 18 valence electron metal alkyl complexes are going to be kinetically inert. So these are the three strategies through which the kinetic inertness of metal alkyl complexes can be increased, so that we can block the beta hydride elimination or decomposition through beta hydride elimination in these metal alkyl complexes, and this allows us to isolate metal alkyl complexes. In fact, these complexes are quite stable. We have already discussed about the stability of these compounds, and that is the reason why metal alkyl complexes in fact act as intermediate in biological processes as well, because in case of this 1-2 shift in isomerase reaction, that is, isomerase reaction is catalyzed by vitamin B12, that is cyanocobalamin, and the isomerase reaction, that is isomerization reaction, essentially. Where a 1-2 shift essentially takes place, that is, alkyl group migrates to the next carbon atom, and this reaction is catalyzed by cyanocobalamin or vitamin B12 that we know you have probably learned in bioinorganic chemistry. And during this process or during this reaction, a methylated an intermediate with methyl cobalt linkage is essentially formed, and this also tells us about the again stability of such metal alkyl bonds or stability of such metal alkyl complexes. Now, another important aspect of these metal alkyl complexes is that when you use perfluorinated alkyl species, that is alkyl species where all the hydrogen atoms are replaced by fluoride, and such species we call perfluorinated species, say for example trifluoro methyl group here. So if you use this as a ligand, then what you see, and if you compare the stability again of this perfluorinated metal alkyl complex with here the hydrogenated metal alkyl complex here, methyl is the ligand over here, and in this case this particular compound is going to be much more stable as compared to the methyl complex over here, because in this case the stability of the metal carbon bond is again increased, or the bond energy of this metal carbon bond is increased by the presence of these fluorine substituents over here, because when you have the fluorinated ligands or perfluorinated ligands over here, and in this case because of the electronegative character of the fluorine atom over here, so the metal will acquire increased positive charge. There will be increased positive charge on the metal center here, and that is the reason why now the metal orbitals are essentially going to be contracted, and or it will not be much more delocalized, and therefore now the energy of these, essentially we can say energy of these metal orbitals will match the energy of the carbon orbitals in a better way, and that is why the overlap between the orbitals of carbon and metal is going to be much more efficient in this case, while as compared to when you have the hydrogens as the substituents in the alkyl ligands. And that is the reason now why, because of the better overlap of orbitals between carbon and metal orbitals, the metal carbon bond in case of perfluorinated substituents, alkyl substituents, is going to have higher bond energy, and such a species where perfluorinated alkyl ligands are present are going to be much more stable as compared to what you have in case of normal alkyl ligands. So this essentially brings us to the end of this lecture. What we have learned during this lecture are some of the important aspects of this traditional metal alkyl chemistry. But we have seen that there was initially during the initial period there was difficulty in preparation of binary traditional metal alkyl complexes, while main group element alkyl compounds could be easily isolated and have been isolated quite long ago, and that is the reason why initially it was hypothesized that the main traditional metal alkyl bond or metal carbon bond in these traditional metal alkyl complexes are much weaker than the main group element carbon bond in main group element alkyl compounds. But when we compare the different thermodynamic parameters of these traditional metal alkyl carbon bond with main group element carbon bond in different in corresponding complexes, what we found that they are comparable strength thermodynamically, and then we can say that these traditional metal carbon bond in metal alkyl complexes are as strong as, or thermodynamically as strong as main group element carbon bond. But the reason why one could not isolate binary traditional metal carbon alkyl complexes in the initial period was because these compounds tend to decompose very easily, and this makes then that is the reason why it was difficult to prepare these compounds, and they decompose through different pathways, and the most important pathway among these is the beta hydride elimination. So we have discussed about the beta hydride elimination, and we also discussed the mechanism of this beta hydride elimination and how one can possibly prevent beta hydride elimination in metal alkyl complexes. That is, we have seen three different strategies are essentially used. The first strategy involves making sure that an olefin which is going to be formed upon beta hydride elimination is, or the formation of this olefin which is going to be formed after beta hydride elimination is energetically or sterically unfavorable, and that we can do by using the Brad's law and by taking an appropriate alkyl ligand where formation of the olefin is essentially unfavorable by the Brad's law. The second approach involved employing an alkyl ligand where there is no beta hydride, there is no hydrogen atom attached to the beta carbon atom, and the third approach involves making sure that there is no available coordination site on the metal center, so that metal cannot increase the coordination number which is required during beta hydride elimination. And by employing these techniques, one could isolate binary metal alkyl complexes as well, apart from other metal alkyl complexes. And then we have seen the reason why perfluorinated metal alkyl complexes have more stability as compared to normal metal alkyl complexes. And with this, let me conclude this lecture. I thank you very much for being with me during this lecture.